Okay. So the next one, I think we may have introduced it and read through it, but we didn't start any examples, but we'll just start from the beginning again. So we're going to talk about the limit comparison test. If an is greater than or equal to 0, and bn is greater than or equal to 0, and the limit of that an over bn equals L, or the limit of the bn over an equals L, where L is both finite and positive. So in other words, if it's infinite or negative, try another test. So it needs to be finite and positive. So if it's infinite or negative, try another test. But then the two series, the summation of an and the summation of bn, either both converge or both diverge. Okay? So I guess the best way is let's actually just get started with one of the examples. So it's the limit comparison test. So kind of like the direct comparison test, we need something to compare this to. So what do you think we're going to compare this problem to? So similar to the direct comparison, we have to find something to compare this summation to. One over what? What do you think we can compare it to? Yes? I would just do 1 over n squared. Are you still copying on the note cards? Would you like a minute? Okay. We ready to move on then? Alright. So we're going to compare the first one to 1 over n squared. Now we're actually going to do the setup like they showed up above. So we're going to do a limit as n approaches infinity. Now you can do an on top or bn on top. So either your original or what you're comparing to, it doesn't matter which one goes on top. Let's write it with what we compared to. So 1 over n squared, that's on top. And we'll do 1 over 3n squared minus 4n plus 5 on the bottom. But we can simplify that. what would that simplify to? If we have a fraction over a fraction, exactly. Okay. Now remember what we're actually doing with this. We're taking the limit as n approaches infinity. So what would be the limit as n approaches infinity of this? Look at your powers, look at your coefficients. 3, exactly. 3. Is 3 finite and positive? Yeah, so you can say finite and positive. So our conclusion, since the summation of n equals 1 to infinity of 1 over n squared converges we can say this one converges, well actually, yeah, converges by p series with p equal to 2. So we're saying this was finite and positive, so now our 1 over n squared, it converged by p series, because we had the 1 over n form and it was to the power of 2. So with p equal to 2, then the summation of n equals 1 to infinity of 1 over 3n squared minus 4n plus 5 converges. Now that one converges by what? 1 over n squared converges by the p series. Yeah, by limit comparison test. Now the reason you check this one is up above because it says if it's finite and positive, then if the an converges, the bn would converge, or if the an diverges, then the bn would converge, the series or summations of both. So that's it for example 1. Yeah, go ahead.
So with this one, does it tell us what it converges to? Like, is 3 the actual convergence, or is it just some number?
Yeah, we don't know. That's the limit of the an over bn, so the one we're comparing to the original, but we don't actually know what it's converging to now. We know by the p series that what we compared to converges. We don't know what it converges to. And then we know that this one converges because of this test, but we don't actually know what they're converging to now. All right, let's go on to the next one then. I'm going to try different markers. Some of these tips are getting really bad. All right, on the next one. What do you think we can compare this one to? What could we compare it to? If we're just paying attention to the front terms, what could we simplify that to and maybe make something easy to compare it to? Kayla? Yeah, 1 over n. So we'll compare it to 1 over n. Now we're going to go through that same process. The limit as n approaches infinity. 1 over n to the 4th plus 10 over 4n to the 5th minus n cubed plus 7. Again, we have a fraction over a fraction. We can simplify this. Not as easy as last time. what do we get this time? One of them is going to be easy, top or bottom. Which one's easier on our answer? Which one do we know right away? The top should, yeah. Top should be 4n to the 5th minus n cubed plus 7, so it's just from the bottom. Now, for the bottom piece, you have to do a little bit of work. It would be what? N to the, okay, plus 10n. Okay. Now, what do we notice about the powers on top and bottom? Okay, so we know the powers are equal there. So if we take the limit as n approaches infinity, we get what? 4. Again, that's finite and positive. So now that tells us we can use the test. It's finite and positive. So if we look back at what we compared to, is 1 over n. How can we determine whether that diverges or converges? Okay, and by p series it does what? What's your p equal to? Okay, so what does that tell you? Diverges or converges? Yes, diverges. So since the summation n equals 1 to infinity of 1 over n diverges by p series with p equal to 1, then your summation from n equals 1 to infinity, n to the 4th plus 10, 4n to the 5th minus n cubed plus 7 diverges by the limit comparison test. So that beginning part where we took the limit up here is just telling you whether you can use the test or not. Okay? If it is not finite or positive, you would have to find another test, and you're not able to come up with this conclusion. Are we okay with that example? All right, let's go on to letter C then. What do we want to compare this to? Yep. 1 over n cubed. So again, set up like before. Limit as n approaches infinity. 1 over n cubed. 1 over n cubed minus 2. Again, that will simplify pretty nicely. After you simplify, what do you get as a limit? Let me know when you get it. Find a limit?
1.
Yeah, the limit ends up being 1. Is that finite and positive? Yes, so we can go ahead and use the test. So now, look at what you compared to. What test can we use on that? P series once again. And we know that it does what? Okay, it converges. So go ahead and write the same conclusion as we did for like number 1. Since the summation of 1 to infinity for 1 over n cubed, it converges by p series, because your p is what value? 3. It's greater than 1. P is equal to 3. So your summation of the original also converges by the limit comparison test. So 1 over n cubed converges by the p series. So that tells you that your summation of the original also converges. Any questions on this example? I personally feel that these ones are a little more straightforward than some of them. They seem a little easier. I don't know if it's because we've gone through some of the tests already and you have the idea of what we're looking for, but I feel that once you get to this point, it gets a little easier. All right, let's go into the last one. We want to compare to what? Yes. But keep it as the power. 1 over n to the 1/2. That's exactly what we're trying to do. Because what is the power on your n at the bottom? Yeah, it's the square root or 1/2. So yeah, that's what we're going to compare it to. Very good. So again, go through the same process.
Power on the bottom, because this is a polynomial, so you can't just like separate them.
Well, we're not going to separate it. The whole thing is to the 1/2 power.
Yeah, so isn't n just to the 1? How do you know to put the 1/2? Like, I'm not doubting that like you're doing it wrong, but like, how do you know to put like n to the 1/2 rather than n to the first, since that entire bottom is the 1/2?
I know what you mean. Like, you can't just say that this 1/2 goes with this and the 1/2 goes with that.
So why not?
But I'm not sure quite how to explain what you're at. I know what you mean by that. How do you know, like, the 1/2 is with the n? But I guess the best way to think about this is the closest thing we can come up with to compare it to. We know that this 3n minus 2 is going to 1/2 power, so we know this power in the end isn't 1. Something else is happening to it.
Yeah.
And the closest thing we know that's happening is the square root, or the 1/2.
So we're just taking a guess.
Yeah, if this was the cubed root, I would compare it to 1 over n, or the cube root of n, and change it to the...
So it's not necessarily like the other ones where you're going to get an equal power on the top and the bottom?
I guess not necessarily, yeah. Alright, that's going to simplify 3n minus 2 to the 1/2 over n to the 1/2. But do you see what we did, like why that makes this a little easier when taking the limit here? They're both to the 1/2 power, so you can take the leading coefficient. So the limit's what? Yeah, so finite and positive. And then again, what we compared it to, we have 1 over n to a power, so what test can we use, or how can we determine what the answer is to that? What test? Yeah, p-series once again. So by the p-series, p is the 1/2 up here, so it's less than 1, so what does that tell us? Diverges by p-series, with p equal to 1/2. So if what we compared to diverged, we now know the original sum from n equals 1 to infinity of 1 over the square root of 3n minus 2 also diverges by the limit comparison test. Any more questions on this test? Pretty straightforward. Alright, so on the next test, we'll take a look at it. We're not going to go through all the examples on it today, but we'll take a look. Alright, so the next one is the alternating series test. So basically, it kind of looks like the telescoping series where there's pluses and minuses and stuff like that. But you're going to have an alternating series. So you're going to have plus, minus, and it's going to change every time because you're going to have some power with a negative 1. So every time you go from an even to an odd power, that's when you're going to get the switch from positive to negative. So that's why it's an alternating series. So in general, just knowing that the limit of an equals 0 tells us very little about the convergence of a series. However, it turns out that an alternating series must converge if its terms consistently shrink in size and approach 0. So yes, you may keep adding and subtracting numbers, but those numbers in these alternating series, if they're getting smaller and smaller, you will eventually converge. So the alternating series test. If an is greater than 0, then the alternating series, so here's your an, that's greater than 0, and it's being multiplied by -1, and again, that power, that's going to keep changing. You're going to be subtracting a number, adding a number, subtracting. Or n plus 1, again, is the same thing is going to happen. It's just depending where your n value is starting. It's still going to be alternating, though, because you're going to get an even and odd each time. Converges if both of the following conditions are satisfied. If the limit of an is equal to 0. So again, if you take a limit of something and it's not equal to 0, do you remember what test that is? Okay, that deals with the nth term test. Well, now we're dealing with it if it's equal to 0. Okay? So very similar to the nth term test with that one. And then an is a decreasing or non-increasing sequence that is n plus 1, so the term that comes after, is less than the previous term. For all n greater than k, for some k within z. Okay? So that's just an introduction to it. I don't want to get into any of the examples today because we'll be stuck in the middle of some examples, so we'll cover that tomorrow. We'll go through it again. If you want to take the rest of the class and write down the note card for this one, you could do that, and then we'll jump right into this one tomorrow. Okay?